especially thank you for the organization. So I'll be asked to talk about the effective field theory of gravity. I know the funding for this summer school is running out, but it'll be your job to find funding for the next one. And in 100 years, when you organize it, you'll have a lecturer being able to tell you what's going on the top picture. You'll have a beautiful theory of everything, comprising and unifying all the forces of nature and beyond, and you'll be able to go all the way down. We're not going to do that today. I'm sorry.
They say they cannot hear you.
They cannot hear me. Okay, I'll try like that. Okay, is that better? Yeah? Okay. So for those of you who lost what I said earlier, I gave you the answers of everything. But for the rest of what we're going to do, we're going to have a less grand goal, and we're going to build gravity from the ground up. We're not going to be too specific on what may be the ultimate completion of gravity. It may be string theory, it may be something else that you will come up with, I don't know. But I'm really going to consider gravity as a spin-to field. I'm not even going to go as far as saying that it's a massless spin-to field, although that's the notion we're going to be taking for the first part. And then really see how, as a low-energy effective field theory, we need to build it up. And then in the fourth lecture, we'll see how we can put constraints potentially from some notion of what the ultimate high-energy completion should look like, not very specifically, but some of the assumptions that we want to have. So thinking of gravity as a spin-to field, as a low-energy effective field theory for a spin-to field, the easiest place to start with will actually just get some intuition from a spin-one field. And I don't mean to insult your intelligence. You all know everything there is to know about spin-one fields. But the reason I'm still going to start with that is because it's going to allow us to set up some of the conventions and some of the logic that we'll be using afterwards for the spin-to field for gravity, and go much faster for the spin-to field. So I included then the conventions that I'll be using most of the time. Sometimes we'll be working in Euclidean, but very rarely. I'll mention we were in Euclidean. For most of what we'll be talking about, we'll be living in 4 dimensions with 1 of time, with mainly plus signature. I'll be working in units where the speed of light and the Planck constants are 1, and you'll see those conventions. Okay. If this isn't clear which framework I'm working, just ask me. And we'll start with the spin-one field, as I said, not because particular interest in the spin-one field. We really want to do gravity at the end of the day, but a lot of the conventions and a lot of the systematic that occurs for spin-to field, you can already diagnose them at the level of the spin-one field. So hopefully that will be clear in a second. So let's start with spin-one. You can consider it as an effective field theory. At this level, we know some completions for it, so it doesn't even need to be effective field theory. So first, we're going to see how the Maxwell kinetic term emerges for a spin-one field. So really what I have in mind is a vector field, A mu, which transforms as a vector under Lorentz transformation. So as I mentioned, we have a Minkowski metric eta mu nu, which is a diagonal in my convention of mainly plus signature. And so under a Lorentz transformation, so if I have my coordinates that transform like this is my new coordinate. The Minkowski metric, as you know, does not transform. And my vector, this is the definition of a man vector. It will go under a new vector with the Lorentz matrix. Okay, so at this stage, this is all I'm asking for myself. And I'll use the assumptions of locality, We'll talk more about what goes under the assumption of localities much more in the lecture 4, but for now, I'll just consider some local operators at the level of the Lagrangian, and we'll assume Lorentz invariance. So my vector field itself transforms under Lorentz transformations, but I want to build a Lagrangian, and I want to build a kinetic term to start with for my spin 1 field. So for my vector field, which satisfies these conditions. So I can write down all the scalar operators that I can imagine built out of, I want 2 derivatives of the vector field and 2 vector fields. So this symbolically should go like dA squared. And I can be a little bit more precise in the type of terms I can consider. I'll have a coefficient A1 d mu A nu, d mu A nu, another coefficient A2 for another operator, for instance, d mu A mu d nu A nu. And in principle, I can consider yet another operator, which would be d mu A nu d nu A mu. But this integration by parts is the same as that one. So I can absorb A3 into A2. This, after integration by parts, is the same as d mu A mu d nu A nu. So we can absorb A3 into A2. So without loss of any generality, we can set A3 to 0. Okay? So those are the 2 only operators I can imagine writing down at quadratic order in the field, which corresponds to a kinetic term, so has 2 derivatives, and that is local and Lorentz invariant, unless someone else can find another one. Yeah? Okay, so with that in mind, in principle, I could think of this as the most general Lagrangian for a vector field. And my vector field, A mu, in 4 dimensions, a priori has 4 independent degrees of freedom. So for the next hour and a half maybe, and then tomorrow as well, DOF means degrees of freedom. A priori has 4 independent degrees of freedom, but you know that light has only 2 polarizations. You know that typically you only want the vector field to have 2 independent degrees of freedom. And the reason for that is that at least if you allow your vector field to have 4 independent degrees of freedom, one of them is always necessarily sick. And this is coming from Lorentz invariance. The fact that you have a minus sign here and some plus signs there. You can't, if you have 4 independent degrees of freedom, you can't prevent from some of them coming with the opposite sign kinetic term as some other one of them. This wouldn't be an issue if you were in Euclidean, but in Lorentzian, this is always an issue. One of them is always sick if you have 4 of them. So you can see that by looking at the kinetic versus the kinetic versus the gradient energy. So you've probably seen that in a course you may have had. In the interest of time, I'll just, sorry. Okay, in the interest of time, the way I'll present it is by splitting the 4 degrees of freedom into some transverse mode and some longitudinal mode. You can show it in different ways, but I suspect the other ways is more the way you've seen it when you've been introduced with a vector field in quantum field theory, or even classical field theory. So you can see that by performing, this is a split of your vector field A mu into a transverse part and then a longitudinal part, such that this is transverse. And now if I focus on the longitudinal mode, then the Lagrangian I wrote down earlier for the kinetic term, now I'm just going to write it for chi. It has a term which is A1, and the first term looks like d mu chi squared, and then the second term I wrote down, it looks like d mu chi d nu chi. So performing some integration by parts, this corresponds to A1, A1 plus A2 box chi squared, where throughout everything we'll be doing, eta mu nu, the box is the Lambert operator, which I will write like this here in flat spacetime. When in curved spacetime, you really want to put the metric in there. And so you see that if you write an arbitrary kinetic term with A1 independent from the coefficient A2, so those two operators being independent, you will have some higher order derivative terms at the level of your formulation. So that corresponds to you have higher derivative in chi, and what you may or may not know from Strugatsky theorem, these are related to instabilities. And not any type of instabilities, not a tachyonic instability which could be tamed with a particular scale. It's actually a ghost-like instability. The way to see that is that, for instance, you can see this box squared. The propagator for that field chi will go like 1 over box squared symbolically, and you can always write this down, split it down as a limit of 2 massive propagator in the limit where the mass goes to 0 as 1 over box plus m squared. Sorry, there's a minus here. There's 1 over 2m squared here. Minus 1 over box plus m squared. So this is just a trivial mathematical statement. You can do that in Fourier space if you want to. So you can see that hidden in this box squared operator here, the equation of motion for chi will involve a box squared acting on chi, are actually 2 degrees of freedom. One which has the right sign kinetic term and the right sign mass term, so that's fine. The other one has the wrong sign mass term, so it is a tachyon, but that's not really the issue. The issue is it also has a wrong sign. It comes in negatively in terms of its kinetic energy. So hidden in that chi degree of freedom, there's actually 2 degrees of freedom, one of which always comes in with the wrong sign. And so you could switch the overall sign here, but then that one will end up being a ghost as well. So there's 2 degrees of freedom hidden in chi. You can see that a little bit more clearly if you wanted to by writing this Lagrangian for chi, at the moment it goes like that. Let me take the A1 plus A2 out for a second. This I can always write down in terms of two field, chi tilde box chi minus a quarter chi tilde squared. So now you have a Lagrangian for two fields, chi and chi tilde. You can determine the equations of motion for chi tilde in terms of chi, plug it back in, and you'll see that you end up with that. Okay, you can just do this. So you see if you take the equations of motion with respect to chi tilde is equal to 0, that tells you that chi tilde is equal to 2 box chi. You plug that back in, and you get that thing in there. Now, in here are 2 degrees of freedom, but because the kinetic term for those 2 degrees of freedom is just in the is in the off-diagonal term, the cross term, there's no direct terms, you can see that the determinant of the kinetic matrix was always going to be negative, or you can see that directly by diagonalizing. So let me just diagonalize here. And writing chi is our field phi 1 plus phi 2, and chi tilde is a field phi 1 minus phi 2, so that this kinetic term gets diagonalized, and then in this kinetic term for chi, from the first term, you see that you get phi 1 box phi 1 minus phi 2 box phi 2, and then from this you get the masses, the cross masses. So no matter what you choose for A1 plus A2, so long as it's non-zero, you always have 2 degrees of freedom, one of which has the wrong sign kinetic term. So what happens really when you do this split, the typical 4 degrees of freedom that are present in your vector field, they split into 2 degrees of freedom in your transverse mode, and then 2 degrees of freedom in your longitudinal mode. The sort of longitudinal mode and the ghost riding on it. Now this ghost, it is a wrong sign kinetic term. The issue with this instability is that the scale of the scale associated with instability is the kinetic, is the momentum itself. So it's very unlike a tachyonic instability, where you may have a potential which is tachyonic and relating to an instability, and you can tame this instability by making that potential as flat as possible, and that would tell you how fast you go away from the vacuum or from the situation you want it to be in. Here, the scale associated with this instability is the momentum themselves, so there's nothing preventing you from generating more and more of those instability and making it arbitrarily fast. So the only way to prevent this instability is to what? Thank you. Yes. We're going to go into massive gravity, and I'm happy you're embracing that idea. Yes. That wouldn't help though for the kinetic term, right? Or you want to add a mass directly for one of those modes? Is that what you want to do? And preventing from being excited? You could do that in principle. Yes. You can, but how do you put it? Because this has no scale. Yes, yes. And you know the answer because that's the way you always seen it. You set this to 0. You don't allow yourself for a generic kinetic term for your vector field. You really enforce the Maxwell one. And from there derives the U1 symmetry. So this is not the way typically you've seen it. You first start with the U1 symmetry because this is what is observed in nature for the photon. And then based on that symmetry, you build up your Lagrangian. But you can also just consider what would be the most general kinetic term for a vector field, and just the notion of stability itself forces you into the notion of symmetry, in this case the U1 symmetry, just from stability considerations. And that would be the case if you added a mass term for your vector field as well. Okay, so in here, for the kinetic term, the only way to make the theory of a vector field consistent, and that's independently or not on whether or not you want a mass, is to set A1 is equal to minus A2, and I think I want to set it to be equal to minus a half in here to have the right convention. And from there, chi entirely disappear. Yeah, that's true. Disappears from the kinetic term. So you can see it here. We focus on the pure chi kinetic terms, and the pure chi terms it completely disappears if you set that to 0. The cross term will also disappear because A mu transverse is transverse, and so there won't be any cross term either. And since it entirely disappears, it means that performing this split corresponds to a symmetry, and this what tells you that the kinetic term is endowed with a symmetry, enjoys a gauge symmetry, which is nothing other than the U1 gauge symmetry. And that symmetry is what allows you to go from 4 degrees of freedom to a symmetry leads to a first-class constraint, removing 2 degrees of freedom, so you are left with 2 degrees of freedom for, in this case, your massless vector field, just like a photon has only 2 degrees of freedom. And of course, the resulting structure for the kinetic term is what you know. It's just the Maxwell term, F mu nu squared, where F mu nu is d mu a nu minus d nu a mu, as you know it, and it has the U1 gauge symmetry. Okay. So for instance, you could always set yourself into a gauge, use this symmetry to set yourself into Lorentz gauge, where d mu a mu is equal to 0, but you don't necessarily need to do that. So this was for the kinetic term. Now, in principle, I could decide to add a mass term. You may or may not want to do it, and for gravity, we're not going to do it to start with. I will only do it if I have time in lecture 3. It'll depend a little bit on how fast we go. But here, it will be useful to still add a mass term. So we're going to because it'll introduce some of the concepts that we will need in any case. So for our program mass term, for our vector field, the linear order, you still want to keep the same kinetic structure, right? It's not because we have a mass term that the kinetic term has to be different. We haven't determined whether we wanted to have a mass term or not when we included the mass term, the kinetic term. The kinetic structure has to be the same, and now I'm going to add myself a mass term. In this case, there's only one term I can imagine write it down, which is like this. And then the normalization is just a convention. Now, of course, as soon as you add a mass term, your U1 gauge symmetry, which is present for the kinetic term, is broken at the level of the mass term. And that tells you that you have an additional degree of freedom associated with this breaking of the symmetry. And so a massive vector field typically will have 3 degrees of freedom. If it's massive, then it doesn't need to propagate at the speed of light. So you'll have a degree of freedom associated with the longitudinal mode of the vector field. So you'll still have 2 degrees of freedom associated with the transverse modes, if you want. And then 1 degree of freedom associated with now the longitudinal mode. Again, we can make that statement a little bit more precise by saying that even though we are breaking a symmetry with a mass term, we can artificially restore it in a sort of trivial way using the Stueckelberg trick. So Stueckelberg was a very deep person, but the trick itself is very trivial. It's simply to say, just to make my life a bit easier, I'll write it like this. Okay, this is my vector field now. I decide to write it like that. So the Stueckelberg trick is to say the Proca action is not itself U1 invariant in the sense of A tilde mu goes to A tilde mu plus D mu chi. This is not D mu, to write it, sorry, psi, sorry. This is not a symmetry. However, I can write it in a way for which a symmetry is explicit for some of the degrees of freedom. That's the Stueckelberg trick. I write down now my vector field A mu as A mu plus D mu chi. So this is just a way I want to write my field. I can do that. And now manifestly, I have a U1 gauge symmetry for A mu going to A mu plus D mu psi. Let me write over M here. And then chi goes to chi minus M psi. So it's a triviality, right? A tilde doesn't change under that. But of course now A mu itself enjoys a symmetry. So there will be 2 degrees of freedom hidden in that part, and then 1 degree of freedom hidden in this Stueckelberg mode. So there will be 2 degrees of freedom in A mu and 1 in psi. And because I have a gauge symmetry for A mu, I can choose any gauge I want for A mu if I wanted to. And the Proca action in terms of these Stueckelberg fields is given by minus a quarter F mu nu squared, now for this A mu, and it has a mass term as well. You have a cross term. Have this form, and then I wrote the M here, I normalized it. The kinetic term for chi is hidden in here. That's why I normalize it in there so that I can have a canonically normalized kinetic term for my field chi. So this is the Proca action in the Stueckelberg language. Because I have a gauge symmetry for A mu, I could in principle set myself to Lorentz gauge where this is equal to 0. And so in that gauge, there's no mixing between the two. But overall, it should be gauge independent in this framework. So this is a more of a generic statement. And you can see explicitly here that you have your gauge field hidden in there with 2 degrees of freedom, and then your longitudinal mode present in here. Okay? Now I'm going to look at interactions with external sources for this vector field. And once again, I emphasize that even though for the Prague field, I'm losing the gauge invariance, the kinetic term still has the same structure as compared to what you had if I had the gauge invariance. So it's still a Maxwell structure. And this is enforced from the outset by the absence of instabilities. Thanks. So we'll see later how when you have ghosts that are coming suppressed by some scale, you can think of that scale as corresponding to the cutoff of your effective field theory. But here we're not there quite yet because that's already in defining the linear theory itself, not even at the level of interactions. So now let me look at interactions for this spin 1 field. It can be massive or it can be massless. It doesn't matter too much. Let me just do it massive first, and then I can take the massless limit. So I don't need to do 2 things. And I'll just consider external sources. So sources that don't have their own dynamics, not expressed as their own degrees of freedom, but you know very well how to couple electromagnetism or to couple Prague theory to other dynamical degrees of freedom. Okay? Okay, so I'll consider, I implement a source term to the Prague action. I'll start with a massive case to start with. I can write it like this. And if I perform a Stueckelberg trick, which I can or not do, but it's useful sometimes if I do, I can write it as G tilde mu minus 1 over m d mu chi G tilde mu. And if I want to be able to recover a smooth massless limit, it better be the case that this is equal to 0, or at least it scales like m. Yeah? So to recover a smooth massless limit, we need a source to be so that this is 0 in the massless limit, or in other words, it has to scale like at least 1 power of m. I can make that a little bit more precise if we want to. I'm going to split my source again as a transverse source, so a conserved source, and then something that goes like that, where d mu j mu is equal to 0. And I write it like that so that in the massless case, I know that I need to have the sources being transversed. This is just coming from the equivalent of the Bianchi identity, or the conservation of the source. Okay, so written like this will correspond to minus a mu j mu minus m d mu a mu j, and then plus chi box j. Now I'm interested in considering the exchange amplitude mediated by a massive or massless vector field between two sources. So one source J mu and another source J tilde mu prime. So I have a source here, J mu. I have another source there, J tilde mu prime. So it can be some charges there, whatever you want. And then they will communicate through the interchange of the vector field coming into the two. So in principle, if it's massive, that's mediated through the gauge invariant mu or the transverse mu and the longitudinal mode chi hidden in there. Whereas if it's massless, it's just one of them. But we'll say that for the case of a vector field, we recover a smooth limit between the two. So if I include this source term for my vector field, the equations of motions, or maybe I should tell you what this is. Sorry, let me go first into, yeah. So you can consider, no, actually let me do it like that. The equations of motion for A mu tilde sourced by J tilde mu are box minus m squared A mu is equal to J mu, and then box chi is equal to box J. And I think, sorry, I should have said this is in Lorentz gauge. So I can use my gauge freedom to set that. I don't need to, but it's a little bit easier. Otherwise, I have other terms going along. Okay, and the gravitational exchange, sorry, not yet. The vector exchange amplitude between those two sources, I'll do it in the massive case first, but you don't need to. So in the massless case, you just have the first line with m is 0, and the second line does not exist. So a priori, things are a little bit different in the massless case, but you'll see that the end result is just a smooth limit from the other. So you'll have your A mu tilde sourced by J. This is what I mean by this bracket. It's sourced by J in this sense. And then the other source. So this is what I want to picture in here. So one source induces a field which will then allow you to communicate with the other source. Now just substitute the equation of motion from here. I can do that split, which is A mu plus 1 over m d mu chi, and then J mu prime plus d mu J prime. And many terms cancel. For instance, those cross terms cancel out. And at the end of the day, I'll have a contribution mediated by A mu, which is just the transverse, the conserved part of the sources communicating with one another. And a priori, I have the other part of the source, the one which are called as J here, which communicates via chi itself through here. But that cross term here will vanish. So you have d for x, and then the first part, J mu, the A mu, to understand high couple, is just the inverse propagator, box minus m squared. If you're not happy with that, you can do it in a Fourier space, J prime mu. And then the other part coming from here, I have this 1 over m that cancels, sorry, there should have been a little m here. There was a little m there. So that will cancel the little m there to cancel each other. And then end up having
minus chi box J prime, which I can write as, sorry, it starts its life like this, I should say, d mu chi, d mu J prime, which I can write as box chi J prime. The box chi is box J, so this is a box J coming in here. Sorry. I have that. And then this thing here, I can write it as d mu J, d mu J prime. You see that a key difference between this second term and the first one is the absence of propagator. In this case, we can see directly that there's a propagator of the gauge part of the vector field, which mediates between the two sources, whereas here there's no propagator at all. There's not really any exchange. This is just going to give you a boundary term, so nothing physically relevant in this term. And so in the massless limit, you see that you recover here, the mass is zero, the mediation between just the conserved part of the sources, which is just the same as what you have in the massive case when you take the limit where the mass goes to zero. So there's no mediation in this part there. You recover a smooth massless limit up to this term, which contains no propagators. So in the limit m goes to 0, you have d for x j mu 1 over box j mu prime. And I emphasize that because it would be different in the gravity case. So before we go into the gravity case, very quickly, I just want to give a word of caution on determining the operators that enter in an effective field theory and illustrate it with what can happen in a massless case and what can happen in a massive case. So if I consider an effective field theory for a massless vector, for instance, which has a U1 gauge symmetry, I can write down my Lagrangian. I'll start with what we derived at the linear order, the Maxwell kinetic term, and then in principle, I can write down my effective field theory as any local Lorentz invariant operator, so any scalar at the level of the Lagrangian, which is U1 also invariant, so it will have to be built out of F mu nu. So it corresponds to adding an arbitrary high number of derivatives on derivatives on an arbitrary number of Maxwell field strength tensor, mu nu. So you have indices here, you have indices there, you have to contract them to one another in a non-trivial way. And so a priori you have lots of Wilsonian coefficients there. And then that will come in at the scale 2n plus 2m minus 4, the scale lambda. And so this is the EFT of a massless vector field for which perturbative unitarity breaks down at the scale lambda if all of those Wilsonian coefficients C are of order 1. If one of them is much larger than 1, then it will break down a much lower scale. You can see that, for instance, by considering some amplitude. So you scatter some vector field together, theoretically, at least. And this amplitude will involve lots of loops, including the vertices related to those operators. And they will scale. If here, for instance, I'm thinking of a 2 to 2 scattering amplitude. If I write down S, the Mandelstam variable related to the center of mass energy squared, we'll be a little bit more precise about all of that later, but just symbolically for now. This will go as a sum of those Wilsonian coefficients, and then we'll have some S n plus m. Sorry, I should write it as a, this is not the mass. Over lambda to the 2 n plus p. So we see that if we working at s much smaller than lambda squared, that's all fine. But if you start wanting to consider this effective field theory for processes which involve some energy or other quantities which are physical, which will be related to the cutoff of EFT, you'll see that this will go out of control. More precisely, what you can write down, if you have this amplitude and then you expand it into your partial wave expansion, you'll see that the coefficient of the partial wave expansion are no longer going to be bounded by 1 if you're trying to push your energy to be of order lambda squared, your energy squared of order lambda squared. But unitarity tells you that all the coefficients of the partial wave expansion of this amplitude have to be bounded by 1. So what has to happen as you reach energy scales which come close to lambda itself is that other operators, other new degrees of freedom have to come in to reorganize your effective field theory and allow you for perturbative unitarity to be maintained. Okay? So this is trivial, relatively trivial in this effective field theory because there's just one scale in the game. Now if I consider a massive case, you may be inclined to write it down something like by analogy goes like this. And then, for instance, something that goes like a coefficient A mu to the 4. Since you don't have your gauge invariance anymore from the mass time, you can start adding terms like that. And then a term like 1 over lambda squared, A squared, F mu nu squared, or something like 1 over lambda 4, F mu nu to the 4. And I should say this is for your vector field A tilde. So those are all tildes. And you may ask your question, you may ask yourself, up to which scale is this EFT a good description, plus other sorts of operators like that. So what is the scale at which perturbative unitarity breaks down for this effective field theory. You may think it's the scale lambda. That's the only scale really included, right? But now if you resplit using the Stueckelberg trick your field into its really dynamical degrees of freedom, the ones that are canonically normalized, you see that you have to introduce a 1 over m for the longitudinal mode, so that is canonically normalized in here. And so, for instance, something going like a mu tilde to the 4 itself will scale as 1 over m4 d chi to the 4. And so in this effective field theory, perturbative unitarity will break down at the mass of the vector field itself. It's never a good effective field theory. You have actually an infinite number of scales entering. You have operators coming, not just a mass term, really interactions coming in from the mass scale m all the way up to the scale lambda. You have an infinite number of interactions there with coming in non-trivially at different scales. And you can't even trust this effective field theory at the scale of your vector field because it becomes perturbative unitarity is broken down already at that scale. So this is a bad theory. You can write it down, but there's never any regime where you're going to do anything useful with this effective field theory. Never. It's never going to be the low energy approximation of a meaningful high energy completion on which computing anything with this low energy effective field theory will give you an insight on what may happen, not even perturbatively. Rather, what you should do to build up an effective field theory when you have some mass term coming in, for instance, is the best way to do is to work in the Stueckelberg trick, determine what the scales are in terms of your various modes, and then if you want to, you can go back into unitary gauge. So here it's kind of implicit what you should have done. This A that came here should itself scale like the mass. So rather you should have introduced at least an A, let me write it, an A tilde here, there was an A tilde here, an A tilde here. This A tilde has to scale like the mass to the 4 over lambda to the 4. So what you want to write down is A tilde is equal to A m to the 4 over lambda to the 4. Now you can go back to unitary gauge if you want to, written like this, but this should really be expressed as m over lambda to the 4, for instance. And then you can do the same thing for all of the other ones. Then you will end up with an effective field theory for which the cutoff, or the scale at which perturbative unitarity breaks down, is lambda. I'm making a little bit of this distinction between perturbative unitarity because in principle, one of you could come and say, well, it's just perturbative unitarity that breaks down and things resum in such a way without the need of new physics. This is possible. In practice, it's quite hard to see that happening, but in principle, that could be possible. But what we do know is that perturbative unitarity will break down, and so we would, at the very least, need to find a new reorganization scheme for our effective field theory, or we will need to include additional degrees of freedom for which those operators correspond to the low energy effective description. Okay, so I've taken an hour to do that. Now we can do all the rest in the 1 minute I have left. Yeah, how much time do I have? I have 5 minutes. Oh, gravity is simple, right? Okay, so I'll start the first stage of gravity, the one which looks identical to this vector field theory. And then we'll go this afternoon to the more interesting part, maybe. I don't mean to be offensive to any of my colleagues. Of course, gravity is very different. So for gravity, I'll start with, oh, you can't see it anyways. I have a beautiful slide here showing you everything you need to know about gravity, and you won't see it. No, I'm joking, it's fine, it's fine. So I've been a bit slow here for the vector field. I wanted to emphasize how the stability condition in the absence of ghosts can really be thought together with locality and Lorentz invariance can be thought as fundamental, and from there emerge the U1 symmetry. And the same thing, you can think of it happening at the level of the spin to field or gravity itself. And then I'll start with massless effective field theory. In the case of a spin to field, there's much more differences between the massive and the massless case, so I'll separate them out because not everything is the same in the massless limit of the massive case. So let me start with the same way I started for the for the spin one field, and I'll recover the well-known Linearized operator. So that's the kinetic term, which you may know under the name of the linearized Einstein-Hilbert term. So again, I'm in Minkowski, and then this time I want to consider, I'll say, a tensor field, and I want it to be symmetric, and under a Lorentz transformation, what I require of it is that it transforms as a tensor this on symmetry. The indices is more or less all I require of it for now. And from that, and the statements again of locality and Lorentz invariance tells me that the kinetic term for the tensor field, just a kinetic term, so I'm not going to tell you whether or not I want to add a mass. I'm not going to tell you how I want it to interact with the rest of the universe. I'm just thinking of what the kinetic structure, what type of kinetic structure is possible for this spin to field, or for this vector mode, tensor mode. Symbolically, it has to be, want it to be local, it has to be of this form, where we have various contractions related to how we can make a scalar out of these operators. So I can write it as, for convenience, the alpha h mu nu. And there you can go through the exercise of finding every possible contraction which is relevant up to integration by parts. And you can find 4 of them. You can write them in different ways. I'm just going to write them like this, because it's going to make my life easier in a second. So let me write actually like this. And you can check if you can find something else. The chances are, if you think of any other type of operator you can write down, other ways to contract your indices, it will be equivalent to one of those up to integration by parts. And now we can play exactly the same game as what we did earlier. And I can split my tensor field into a transverse. I'm just going to do transverse for now. I could do transverse traceless. It's a symmetrized version. You don't really need it. Sorry, there's something missing. Sorry. Sorry. Yes, you're right. Thank you. So this is H, and then it's eta nu alpha. Thank you. Yeah. Yeah, thank you. So now I can do the same thing as earlier, and I can split my tensor mode into a transverse part, which satisfies d mu ht mu nu is equal to 0, and then some sort of longitudinal part, although it's a little bit more complicated than that. And what you will see is that in order to avoid having higher derivatives for those, this effectively needs to have the Maxwell term, and then to remove the longitudinal part hidden in here, and then to further remove any higher derivatives acting on this chi itself, you're going to need to specify your coefficient, to tune your coefficients against each other. So this I'll let you do as an exercise. You can see that if you put an arbitrary combination here, you're going to end up with 2 derivatives on chi from that term, and then 2 derivatives on chi from that term with various different type of contractions. So now you will end up with lots of different terms which have 4 derivatives at the level of equation of motion acting on chi. And so removing all of those is the same thing as the tuning A1 is equal to minus A2 as we did for the vector field at the level of the kinetic term. Now it will impose some conditions between the B's themselves, which is B1 is equal to minus B2 is equal to minus B3 is equal to B4. And I want to set it equal to, I think I'm going to want to set it equal to minus a half. But no matter precisely what the overall coefficient is, can you guess what's special about this combination? Yes, exactly. This special combination is going to be built so that chi, any derivatives on chi, disappears entirely from the kinetic term. But chi can only come in with derivatives. It has derivatives acting on it. It can only come in with derivatives. So chi will have to disappear entirely from this combination. But for chi to disappear entirely from this combination, it means that if you take this kinetic term and perform that split, chi disappears. It means that this corresponds to a symmetry, which is linear diffeomorphism. So in order for you to avoid having any ghost in building the theory of a tensor field, a spin-2 field, you necessarily need to have, at least at the linearized level here, linearized diffeomorphism. So this tells you that chi mu disappears, and you force into linearized diffeomorphism is a symmetry of the kinetic term, at least the linearized kinetic term. And the kinetic terms end up being nothing other than the Linearized operator, which of course is nothing other than the linearized Einstein-Hilbert term. And this hopefully you know, because you know that linearized diffeomorphism is just a linearized version of covariance, which is satisfied by the Einstein-Hilbert term. So we cover linearized gravity in some sense, or the linearized Einstein-Hilbert term. Now we'll be nonlinear from there. Yeah, I'll finish it. Yeah. My time to shut up.
One quick question before we split for coffee, and then, of course, Claudia has to
So when you were talking about this practical unitarity, or this unitarity, kind of uses calculation at the top board here as an example with the 4 A's interacting.
Yeah.
So my question is, how does that interaction, can you explain how that is connected to this idea of perturbative unitarity?
Oh, so you have an amplitude associated with that? And then from so I'm not entirely sure what your question is. Maybe it's how does unitarity manifest itself at the level of this amplitude?
Yeah, I guess I would just assume, like you were saying, up to some order, the equations you're dealing with have like a unitary symmetry, but I guess you're saying that this computation somehow shows that
So
this
you'll
doesn't?
see very
certain
very
scale?
symbolically, and we'll go through that more precisely, but very symbolically here, what you see is that the amplitude itself is starting to be large, starting to be larger than order 1. So that's not a very precise statement, but what you can do then is try to understand how this amplitude, you can expand it in a partial wave expansion, and you will see that if this starts becoming larger in this case, the coefficient of the partial wave expansions themselves are going to be of amplitude larger than 1. And you know that this is just impossible. You know, unitarity imposes all the coefficients of the partial wave expansion to be bounded by 1 in amplitude.
Okay, thank you.
We'll go through that more precisely, that this is just a very quick back of the envelope way to see things are getting out of control. And I'm using the terminology perturbative unitarity there, which may seem like this is only applicable at the level of the quantum field theory. But at the classical level, you see that the perturbations are coming out of control. They are not small. They're not perturbative. So if you just want to take this as a take-home message, just take that, yeah.
Okay, thank you.